Hello, everybody, and welcome. My name is David Mann. I'm an Associate Professor at the Centre for Longitudinal Studies, and I'm pleased to be joined by my colleague, Liam Wright. So, Liam, do you want to introduce yourself?
Yeah, hello, I'm Liam Wright. I'm a lecturer at the Centre for Longitudinal Studies.
Great, let's make a start. So we'll present and there'll be time for questions and comments at the end. Okay, I'm sharing my screen. So welcome. The title is Cross-cohort comparative analyses in the British cohort studies, opportunities and challenges. Some brief housekeeping. We are recording this session, so it's available online at a later date. If you have a question, please use the chat function. For technical issues, please email us, and please do fill in the feedback form at the end. So here we can see a researcher about to undertake some comparative research across time, and they have ahead of them a long and treacherous road, but it's hopefully helped by the research that's been done in the past and the resources that we can make available to help future researchers. So the overarching aim of this session is to discuss the opportunities, the challenges, and some possible solutions to undertaking comparative research using the British cohort studies primarily. We'll be introducing resources, analytical resources, and data resources to help research in this space. So let's start with some background and motivation. In many areas of science, we're interested in how some population characteristic has changed across time. So for example, in the health sciences here on the left panel, work from Susan Jebb and colleagues documenting the changes across time in a health outcome. So here, the increase in obesity from the 1980s to the 2010. On the right panel is showing a change across time in association between social position, area level deprivation, and obesity in England, showing an increase in inequality in obesity from 1995 to 2007. So both of these approaches principally interested in some kind of change across time in the health sciences. It's also the case that this is a frequent goal in the social sciences as well. On the left panel showing the change across time in the occurrence of population characteristics. So here it is teenage pregnancy rates, which appear to have declined across time. On the right panel, looking at long-run trends in intergenerational social mobility in the US, showing broadly consistent trends over a long period of time. So what does this kind of analysis typically involve? Well, frequently it involves collating and bringing together and analyzing data from multiple sources, ensuring these data are valid and comparable, that we address multiple sources of bias, and that we draw the appropriate inferences. And so what might be concerning is that there's many different analytical decisions along the way, and these could possibly alter the conclusions that we draw. So this kind of work is challenging. And we find that most training is typically takes place with researchers learning to analyze single data sets from single studies. And so this tends to mean that individuals doing comparative research all need to start from scratch to some degree. And so myself and colleagues developed a paper to discuss the challenges and possible solutions of doing this kind of research, and this paper here, and there'll be a link to this in the slides. As part of this paper, we included an optional checklist and we included a teaching resource. And we felt that there's so many different diverse research questions that we didn't give authoritative rules that researchers should follow, but we instead discussed the problems more broadly and gave a range of possible solutions. We should say that this was targeted at researchers that were relatively new to this space. So this is the analytical resources that we provided. We provided guidance on different aspects of comparative research workflow. So we gave syntax in both Stata and in R to undertake descriptive statistics, study specific regressions, and comparative analysis in different cohorts, as well as touching on issues such as missing data and longitudinal data. So with particular thanks to Liam for leading on this resource. The link is available in the paper, but this is just to show you what it looks like. This is the resource in R programming language, from descriptive stats to multiple cohort analyses. This is further analyses in R, and also analyses in Stata here, doing a meta-analysis of multiple different cohorts. As part of the paper, this is the checklist which we hope researchers might find helpful when they're undertaking this kind of research. So thinking about the different components that might be helpful to include in comparative research, from the introduction, the methods, the results and sensitivity analyses, and the discussion section of papers. So let's move on now. We're going to be talking about the various different challenges and possible solutions, ranging from the studies that we include to how we interpret the associations that we do find, and whether we do or we do not draw causal inferences from these associations. The first consideration then is somewhat obvious, is the type and the span of studies that we include. Well, here at CLS, Centre for Longitudinal Studies, we run a series of cohort studies. So the oldest of which was, they were individuals born in 1958. So individuals born in a single week of 1958 were enrolled in a longitudinal study, and they've been providing data since they were babies, across their infancy, their childhood, their adolescence, and across their adult lives. So we have very rich longitudinal data, and this is the birth cohort design. We have multiple different birth cohorts, born in 1958, 1970, and the millennium, and we have a study called Next Steps, individuals born in 1989 and 1990, who have provided data since they were in adolescence onwards. So from these data sets, we can undertake comparative analysis across a long period of time, across many different decades. And we can also undertake longitudinal analyses within cohorts as well. Our website provides more information on these resources, which are freely available to researchers, anywhere in the world. We have introductions to the different data sets, to the 58, the 70, Next Steps, and the Millennium Cohort study as well. There is a broader range of longitudinal studies in the UK, ranging from regional studies like the Hertfordshire Cohort study to occupational cohorts, so the Whitehall study, and panel studies like Understanding Society. So many of these can also be useful to examine change across time. So we include this in the paper, and I'm just going to show this slide rather briefly, that we are fortunate in the UK to have a range of cross-sectional studies and longitudinal studies to compare across time, and we can compare across time in the UK, in Europe, and in other continents, like, for example, the US, with the NHANES study and their panel studies as well. So one consideration is the possibility of getting complementary information from different study designs. So let's say, for example, we're interested in comparing adolescent mental health. Then at a particular age point, we want to compare adolescent mental health. And we can do so using both cohort studies and cross-sectional studies. And each of these has complementary strengths and weaknesses. On the cohort studies, we have temporal ordering. We're able to examine age-related changes in an association. And we tend to have a larger sample size at a particular age. That might be helpful for adolescent mental health. It might be helpful for looking later in life at key age points, for example, in midlife health or in health and functioning in older ages. We can do the same comparative analysis in cross-sectional studies. And these are beneficial because we have an updatable target population. The samples may better reflect demographic changes, for example, migration, which occurred after the initiation of cohort studies. We tend to have a greater spread of years in these studies, enabling a greater chronological precision, and we have a greater spread of ages. And so some examples of doing this in practice is some work that myself and colleagues have done with body mass index. And so the first was a paper examining trends in inequality in body mass index according to education level. On the right panel, we see evidence from the Health Survey for England, looking at educational differences in systolic blood pressure between 1994 and 2016. And we see evidence of a persisting association, potentially increasing in strength across time. Across all adults, those with lowest education had highest systolic blood pressure. We do a comparative analysis in the birth cohorts, and we find a similar story. So in the 1946 cohort, in midlife, those with lowest education had higher blood pressure. This association was also found in the 1958 cohort and the 1970, and somewhat higher in those cohorts. And in the cohorts, we're able to examine the associations of childhood and adult social class, as well as education as well. providing us evidence of the cumulative associations between social disadvantage and health that we're less able to do in cross-sectional studies of adults. So this is an example of where the two studies find similar results and we're triangulating on some kind of conclusion, and we're taking advantage of the relative strengths of the different approaches to address the research question. It's also possible that we get a different answer when we examine the cohorts and other study designs as well. We have a previous paper from colleagues in UCL which compared two cohort studies. It compared the 1958 and the 1946 cohort, and it found across time that there was a strengthening of the association between body mass index and blood pressure. So typically individuals who have a higher body mass index have a higher blood pressure, have a higher hypertension risk. And so because BMI has increased across time, it was rather alarming that the correlation between these two health measures has increased across time. That suggests that there could be an even worse impact of the obesity epidemic than the increase in obesity alone. But how robust, we were interested in understanding how robust was this trend across different birth cohorts and across different cross-sectional studies. And so on the right panel, we replicate the previous work showing an increase in strength of the association between blood pressure and body mass index between the 1946 and the 58 cohort, and it was stronger as well in the 1970 cohort. When we look at the Health Survey for England, we find a rather consistent patterning of a declining strength of association, so there was no increase in association. And we concluded in this paper that the increase that was reported in the past was likely due to the methodology of the blood pressure measurement at this particular time point. A different measure was used for measuring blood pressure. And so we discussed in this paper that two time point comparisons can actually get the wrong answer when you're interested in a longer term time trend. More broadly, having a longer time span can be helpful in terms of the research questions that you can address and the inferences that you can draw. So many social science researchers have discussed the decline in community participation from around the 1960s onwards in higher income countries. So for example, in the US and the UK, we have the book Bowling Alone by Robert Putnam and Coming Apart by Charles Murray. So researchers on different ends of the political spectrum, all discussing this similar issue, as well as the more recent Deaths of Despair by Case and Deaton. Of interest, however, is a more recent work by Bob Putnam and Garrett and colleagues, showing over a longer period of time, so from the 1890s and early 1900s, actually showing this increase in community participation across many metrics, adding to evidence that community participation is likely to be modifiable by the environment and by policies. And therefore, just by widening the span of investigation, we're able to understand more about the research that we're focusing on. Another consideration is ensuring that we have comparable target samples and population. So we've discussed the British birth cohort studies. It's worth mentioning that it's considering which included nations and regions are in each of these studies is important when making comparable analyses. So there is another birth cohort study as well, which is the ALSPAC study, which is born around in the early 1990s. And so many studies have compared this ALSPAC study with the national cohort studies that we discussed previously. So an issue here is that these individuals are born in a different birth year, but they're also born in around the Bristol area. So in this sense, we might be at risk of conflating differences across time with regional differences in the UK and with Bristol area itself. This is also the case when we compare the Millennium Cohort study with older studies. The Millennium Cohort study included oversampling of regions such as Northern Ireland, which were not followed up in adult life in the older birth cohort studies. So restricting to a comparable regional area can be helpful in those kinds of research questions. Work from my colleagues Patelet and Gage examined adolescent mental health and its correlates in ALSPAC and the Millennium Cohort study, and used propensity score matching to try and account for the differences between the Bristol region and the broader UK region, and they're able to make better comparisons or fairer comparisons between different generations. Another consideration that there's been an increase across time in the ethnic diversity of the UK. So this plot shows this from 1991 to 2011. The fraction of individuals in England and Wales, which was white, British, was 93%, declining to 80% in 2011. So this is something to consider in analyses, particularly if the association that you're examining, for example, is modified by ethnicity. So in the case of social position and obesity, there was some evidence that this could be modified by ethnicity. And therefore, the conclusions that I drew when drawing from that analysis had to consider that whether this is generalizable to the contemporary population in the UK. So restricting to the white individuals may limit the generalizability across the broader UK, given the changes in the ethnic distribution across time. Another broad consideration is differences in measurement in different studies. This is a nice paper in the BMJ by Hutchison et al., and it highlights how random measurement error might influence associations. If we have random measurement error, we get regression dilution bias. That means that if the random error is on the exposure variable, the effect sizes that we observe are likely to be attenuated. If we have random measurement error on the outcome, the y variable, the association is likely to remain the same, but the effect that there's likely to be less precisely estimated. So the standard errors and the confidence intervals are likely to be wider when that's the case. For non-random or differential error, we can get bias in either direction. Our association can either be strengthened or weakened in some cohorts that have more differential error and bias compared to other cohorts. A possible solution here is harmonization. So we can try and seek and harmonize our exposure and our outcome variables in our analysis. And so the Closer Learning Hub has lots of useful resources on harmonization. Often we find that an issue here is that when you harmonize, you are reducing the information in each of your cohorts to the lowest common denominator, which is available in all cohorts. So for example, you might have very rich data on income in one cohort, but only have relatively crude measures on social class in other cohorts. In which case, a sensitivity analysis can be helpful, so you could then probe and see whether your association is markedly differ when using the richer data available in a smaller subset of cohorts compared to the lowest common denominator in all cohorts as well. As well as the closer resources, there's a number of other resources available around the world which have provided data on harmonized measures across time, and have also provided resources and tools to help harmonization take place in future, including the Harmony Initiative, which seeks to provide a tool to help harmonize mental health measures. But this table is also in the paper. In our cohorts at CLS, we have a range of data sets which have been harmonized by researchers in the past: socioeconomic measures, social class of the parents and the cohort members, harmonized measures on anthropometric measures, mental health measures, and measures of the child environment in different cohorts. And there's ongoing harmonization programs relating to fertility and measures of chronic health. Other options to ensure comparability across time: one option is you can triangulate across different data sources, for example, different types of study and different measures of measurement. So one option, for example, is you could compare using observed exposures with exposures derived from genetic liability measures. So with the increase in availability of genetic data in our cohorts, this could be increasingly possible in future. It's also possible to undertake separate calibration studies. So there's an example of this in the mental health literature, where they take a separate set of individuals and they administer multiple tests, multiple different tests, to try and understand how comparable the tests are. There's also an ongoing calibration study my colleague Vanessa Moulton is leading on, looking at different cognition measures in young people as well. For some outcomes where you have 3 or more indicators and you have an underlying latent trait, which you don't observe, for example, the latent trait of depression, we can look at and use the methods of invariance testing available in the psychometrics literature to try and ensure our outcomes are comparable in different cohorts. Another challenge is missing data when comparing across time. On this panel, we see changes in response rates to health surveys, cross-sectional health surveys in Europe from the 1990s to 2011. We see a declining response rate, and we in fact see this in many high-income countries across all kinds of study designs. So on the right here is the labour force survey response rates declining from under 50% to just under 20% in the most recent year. So this is a concern, and in longitudinal studies, we have lots to follow up across time. So in the 1958 cohort, we have individuals are less likely to be in the study in early and adult life and less likely still in later life. So what this appears to be a concern. What are the specific concerns that might bias our comparative analyses across time? We have more missingness in more recent cohorts. The first major consideration is lack of power in the more recent cohorts. The more concerning feature is the potential bias that this could introduce. It may be that the differences in missing data are leading to strengthening or weakening of associations that we observe compared to older cohorts where there's less missing data. And to handle this, we recommend using principled approaches to handle missing data. So this is using the data that we do have to inform what those missing values might be. This can be using multiple imputation, using analytical weights, or using full information maximum likelihood in SEM modeling. Another point to add here is that in cohort studies, we do have lots to follow up, but we do actually have the early life data to inform the plausibility of how we model this missing data process in our analyses. Each of these principled approaches requires assumptions on the likelihood of the data that we do have predicting the data that we do not have. This is an example which depicts this. If we take the NCDS and we're looking at the percentage of individuals that have a father in the professional social class at birth, the percentage in the complete sample is around 4.5%. If we do the same analysis, but only using respondents that took place in the age 55-year survey, we have a far higher estimate of this social class measure. When our colleagues used multiple imputation, so using the rich early life data to predict missingness to try and reduce the bias, we found that the estimate was drawn back to where it should have been in the first place. More details of this is available in this paper by Mustafa et al. At CLS, we provide a number of resources to help researchers handle missing data in our cohort studies. So we have user guides and we have video tutorials. We also have an event coming up in June on handling missing data in BCS 70. The final point for me is how we compare associations across time. The first consideration is whether we look on the relative scale or whether we look on the absolute scale. So for example, the relative scale of association, we might be looking at a relative risk or an odds ratio, or an absolute scale, we might be looking at a risk difference. And it's been shown in the health inequalities literature that it really matters the scale at which you examine your association across time. So for example, since mortality has declined across time, the absolute difference between SES groups has in many cases remained the same, and this has resulted in there being an increase in the size of the association on the relative scale. That's depicted on this right-hand side panel. A more intuitive example is this here. So the prevalence of cigarette smoking by social class, the absolute difference in the 1970s was similar to the absolute difference in the early 2000s, but as a fraction of overall percentage of individuals smoking, this is a smaller fraction of the total than this is. So it would appear that the relative inequality have increased in size, despite there being a persisting absolute difference in inequality. We show this in the paper, and we give syntax to examine both scales of association. I find this Twitter account quite useful to get an intuitive understanding of this. It's called Just Say Risks. So thank you to whoever is running this. But for example, it takes out media reports of science. So here it shows in a new analysis, researchers report that the number tripled from 2016 through to 2019. So a tripling of something of gender affirming surgical procedures. This account shows it on the relative scale, which is shown in the press reporting, but also on the absolute scale as well. So something that appears to be large on the relative scale may not be so large on the absolute scale in terms of how many actual individuals have gone through this compared to in the past years. So how do we? That's about the scale. So let's assume that we have we choose the appropriate scale, and perhaps we look at both scales of association. Well, how then do we compare cohort differences in association? One option is simply to do this informally by presenting the estimates alongside each other and looking at how precise those estimates are and the extent to which the confidence intervals overlap. We can also directly compare our estimates, so we can pool multiple cohorts together and we can include and test interaction terms, so the exposure times cohort study interaction term. However, this isn't always possible, so some studies vary in their sampling design, which makes it very difficult to run a pooled model, or they can't be accessed outside of specific trusted research environments. So in this case, we can indirectly test, so we can do meta-analyses, we can get our study-specific estimates, we can output them, and we can compare them in a meta-analyses framework. I'm now going to move over to Liam to talk about interpretation and causal inference in comparative research.
Okay, yeah, so I'm going to first talk about interpretation. If we do find a difference in association between contexts, the question then is, how should we interpret the results? I'll discuss this with a hypothetical example where we're interested in cross-cohort changes in the association between education and obesity. Now, one explanation, and probably the one that we're most interested in, is effect modification. The association differs because of a change in the causal effect an exposure has on an outcome. This might be because the links on the causal path between the exposure and the outcome have weakened or strengthened. For instance, education may be more strongly related to obesity in settings where the education wage premium is higher. It may also occur because new pathways have arisen or have been removed. Again, looking at the link between education and obesity, this might occur when new technologies become available and aren't adopted evenly across society, such as what appears to be happening with the new availability of the weight loss drug Ozempic. But this isn't the only explanation, possible explanation rather. Importantly, differences in the confounding structure may occur over time or across contexts. This is particularly important where the prevalence of an exposure changes dramatically across contexts, as has happened with the expansion of education. The exposure may be more or less correlated with the confounding factor, or the effect of the confounder upon the outcome may strengthen or weaken across time. Each would generate differences in association across contexts. For instance, as education has expanded, its association with socioeconomic background and cognitive ability has changed, and this has important consequences for education's association with health outcomes such as obesity. Differences in selection may generate differences in association across contexts too, though this is more to do with the characteristics of the sample and data that are being used than underlying social change. Studies of different recruitment and attrition rates and vary in how well they represent the general population. This could lead to differences in association that are an artifact of sample biases rather than changes in society. As David has noted, it is well observed now that response rates have declined dramatically over time, particularly following the COVID-19 pandemic. If education and obesity are both related to selection into a sample, they will become associated purely mechanically. This is an example of what is known as collider bias. And to help explain collider bias, I'll give a quick classic example, which is the negative correlation between physical attractiveness and acting talent among Hollywood stars. Hollywood stars are either good looking or good actors. We don't see bad looking bad actors because they don't get hired, but the good looking bad actors and the bad looking good actors do. The negative association we observe is merely driven by the data points we see. Now, changes in the underlying distributions can also affect selection. As has been shown before, obesity rates have increased. If obesity per se is similarly related to non-response across time, we'd still have greater degrees of selection bias in more recent cohorts because there is more obesity about. As David has also mentioned, we can get differences in association because of differences in measurement. On screen, we see the association where there is random measurement error in the exposure variable that we have measured. This leads to regression dilution, so an attenuation between the association for the measured exposure and the outcome, because each unit change in the measured exposure only partly reflects change in the underlying latent construct. In our current example, education may be measured less well in some studies than others. For instance, exact age at leaving education in one study versus highest education level in another, and this could explain differences in association. Other forms of measurement error can also generate differences between samples. On screen is an example of differential measurement error in our outcome variable. The measurement error is related to the level of the exposure. Excuse me. For instance, we may use self-reported BMI in one study, and the accuracy of the reports may be related to one's education level. This creates an association between the measured exposures and the outcomes, not related to the causal effect of interest. Next, I want to discuss how cross-cohort and comparative research can be used for causal inference. So on screen is a directed acyclic graph, a DAG, reflecting the usual situation in observational research. We want to know if some variable X has a causal effect on some outcome Y, but there is a potential confounder Z that could explain any association between the two. Comparative research, comparing across time or between populations, can offer some opportunities to make causal inferences in this situation. So the first opportunity is to make comparisons with populations in which we know a priori that there is no causal effect between X and Y, as represented in the DAG on the right-hand side. Two examples should make this clearer. So on screen is the time series of the teenage pregnancy rate in England since 1998. Between 1999 and 2010, the UK government implemented a teenage pregnancy strategy, which cost hundreds of millions of pounds. And because of devolution, this strategy was only implemented in England. Did the strategy reduce pregnancy rates? Well, some have argued that the decline after 2007 demonstrates that it did. But if this was the case, we would also expect the decline in teenage pregnancies to be far faster in England than Scotland or Wales, which did not have similarly resourced strategies. That we don't see this, and in fact that we see very similar trends with a buckle around 2007 in those other nations, might give us pause before concluding that the teenage pregnancy strategy was a success. Note that evaluating the teenage pregnancy strategy could be done with another comparative design. For instance, we might compare the teenage pregnancy rate with the pregnancy rate for people who are a bit older who weren't exposed to the strategy. Here's another example, and this time we're going to look at some individual level data. So one large area of research is on the effect that alcohol may have on various health outcomes. Researchers have used genes related to alcohol metabolism as instruments for alcohol consumption. Basically, they make it more or less comfortable to drink. So on screen are the p-values for associations that these genes have with several biomarkers using data from Chinese men. Now, several of these associations are statistically significant, but it could be that these genes have effects through other pathways than alcohol consumption or different traits as well. However, culturally, few Chinese women drink, so we wouldn't expect these genes to have effects on outcomes among this group. And that's actually what we see in practice. The p-values are not statistically significant, making a causal interpretation of the male results more plausible. A related design is where we compare associations using time periods where we expect causal effects not to exist. A nice example of this comes from Sean Clouston and colleagues, who created a model called the social history of disease. They argue that socioeconomic inequalities in specific health outcomes should only arise where technologies or knowledge become available. As they argue, these are taken up more rapidly and in greater numbers by those in more socioeconomically advantaged positions. So this model, it lends itself to comparative research, comparing populations over time. Their theory predicts associations between socioeconomic position and health only in certain time periods. So for instance, this period where it says natural mortality is you would expect no difference between socioeconomic groups because there's nothing known about a particular disease, so people can't prevent it or treat it. Note that these study designs are related to Ronald Fisher's advice to make your theories elaborate in order to make causal claims from observational data. By making your theories elaborate, Fisher meant to draw out all the predictions of your theory and compare these, a set of predictions from competing theories. A causal effect may be absent in a context where confounding should remain, or vice versa, as I'll discuss later. A related design to those just discussed exploits situations where units are treated to differing extents, rather than being treated or not. Again, if confounding is similar regardless of treatment strength, comparisons across contexts can aid causal inference. For example, one question in drug research is whether cannabis causes psychosis. An issue for observational studies is that people predisposed to psychosis might use cannabis to self-medicate. Gage et al. In 2016 note that changes in drug potency over time provide an opportunity to answer this question. Psychosis rates should be highest when THC, the suspected psychosis-inducing element, concentrations are greatest. Another opportunity for using comparative research to aid causal inference is comparing units with different hypothesized confounding structures. Confounding structures can differ between settings in strength or even in direction. For instance, the confounding variable Z might have opposite effects on X or Y in one population compared to another. The example on screen is from a study of the association between breastfeeding and various child outcomes. The authors show that in a UK-based sample, ALSPAC, breastfeeding is socially patterned. So we see that higher income levels have a higher rate of breastfeeding. However, in the Brazilian cohort, which is called Pelotas, there's no such social patterning. So the pregnancy rate is about the same in each social income group, rather. Thus, the association observed in the Brazilian data can serve as a test of the proposition that associations observed in the UK data are merely explained by confounding. In ALSPAC, the UK cohort, associations with blood pressure and BMI were consistent with socioeconomic confounding, and similar associations were not found with the Brazilian Pelotas cohort. But for IQ, associations were not consistent with confounding, socioeconomic confounding in ALSPAC. You'd expect they were consistent with confounding in ALSPAC, but you got a similar size, direction of association in the Brazilian cohort as well. Now, in an even more ideal situation, we might identify a consistent association between X and Y in two populations or time periods in which the direction of bias through confounding is in opposite directions. One estimate would be conservative, the other one anti-conservative, but qualitatively, the two would be in the same direction. Again, similar designs can be used to look across time instead of between populations. Gage note that the SEP patterning of breastfeeding has changed in Britain between cohorts, but the association between breastfeeding and social mobility has stayed relatively consistent. And back to you, David.
Hello, thank you very much, Liam. Let me pull up my slides again. I wanted to just to say, to finish off, before we go to questions and answers, thank you for listening. Can you see this, everybody? Yep. Liam, can you see this? Okay.
Yeah, you can see it.
Great. Okay, thanks for listening. This is a link to the paper. It's also in the chat. And please do check out our website for further training and support. We have further training on handling missing data in June, and we have an introduction to new data, the next steps cohort age 32 in July of this year. If you don't mind, please do the feedback form as well. We know missing data is a problem. Thank you, and now over to questions